Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Master's Degree Programs. Master of Science, Renewable Energy and Environment, MSCRWE. Semester I. MRW 001 Energy Conversion. Block 2 Steam Nozzles and Turbines. Unit 7 Gas Turbine Power Plants and their Performance Characteristics. 7.1 Introduction. The gas turbine prime mover was first used in 1919 for large central station service. Since then several stations have been built with gas turbine to drive electric generators. This is due to some inherent advantages of the gas turbine, such as simplicity and flexibility of design and installation, compactness, low first cost, small building space requirement, little cooling, water requirement, etc. The delivery and installation time for these plants is much less than for steam plants. These prime movers can be started quickly and can be put on load within a few minutes. Efficiency can be improved considerably by employing heat reclaiming devices. However, fuel costs in these plants are usually higher than those in other plants, though maintenance costs are lower than these costs for diesel plants. Since the fuel costs are relatively higher and initial cost lower, these plants are well suited for meeting peak load demands. Applications of gas turbine power plants. Gas turbine power plants for the purpose of power plant engineering. Find the following applications. I. To drive generators and supply peak loads in steam, diesel or hydro plants. 2. To work as combination plants with conventional steam boilers, and 3. To work as combination plants with conventional steam boilers, and objectives. After studying this unit, you will be able to understand the fundamental of gas turbine power plant, working principles of different types of gas turbine power plants, the functions of each component of the gas plant, and the performance characteristics of the same. 7.2 Elements of simple gas turbine power plants. The simple gas turbine power plant mainly consists of a gas turbine coupled to a rotary type air compressor and a combustor or combustion chamber, which is placed between the compressor and turbine in the fuel circuit. Auxiliaries, such as cooling fan, water pump, etc., and the generator itself, are also driven by the turbine. Other auxiliaries are starting device, lubrication system, duct system, etc. A modified plant may have, in addition to the above, an intercooler, a regenerator and a reheater. The arrangement of a simple turbine power plant is shown in figure 7.1. Look at the screen. Figure 7.1, Arrangement of a simple gas turbine plant. 7.2. 1 Gas turbine. Construction. The basic construction of a gas turbine employs vanes or blades mounted on a shaft and enclosed in a casing. The flow of fluid through turbine in most designs is axial and tangential to the rotor at a nearly constant or increasing radius. There are two types of blades used in all turbines, those that are fixed on the rotor and move with the shaft, and those that are fixed to the casing and help to guide and accelerate or decelerate the flow of fluid, being called fixed blades or vanes. A stage is formed by the combination of a row of fixed and a row of moving blades. The power of the turbine depends upon the size, shape, and the speed of the blades used. Multistaging is employed to increase the power output of the turbine by placing additional sets of fixed and moving blades in series. The moving blades may be mounted on one or more wheel or on a drum, and the assembly is called a rotor. For high-speed rotors, solid wheels are employed as a hollow construction weakens the rotor against centrifugal stresses. The rotor may be mounted on a shaft or may be an integral with it. To prevent leakage of gas along the shaft, gas seals or glands are provided where the shaft emerges from the turbine casing. The extending lengths of the shaft on the two sides of the turbine are supported on journal bearings which also maintain it in proper alignment. Axial loads area taken by additional thrust collars, and the turbine shaft is connected to the load with couplings which may be rigid or flexible. The advantage of using flexible couplings is that axial movement or slight misalignments are accommodated within the coupling itself, and are not transmitted to the driven shaft. The dynamic balancing of the turbine rotor is very important for its satisfactory performance. The turbine casing provides the connection between the gas ducts for inlet and exhaust, and the turbine rotor. It also supports the fixed blades and provides the enclosure for containing the fluid under pressure during its passage through the row of blades. To allow easy access to the rotor, the turbine casings are made in horizontal split design. It is necessary that the connection of the rotor with the bearing is rigid enough to maintain correct alignment of the rotor during operation. The size and shape of the casing necessarily depend upon the size and shape of the rotor, and it is important to maintain radial symmetry of the casing to conform to the symmetry in the rotor. The turbine blades are given a rake in the direction of motion, with the result that the centrifugal bending stress is opposed by the gas bending stress. The construction of the blades for high-speed rotors provides the tapered shape with less metal at the tip where centrifugal force is maximum, and more metal at the base to resist bending and tensile stresses. The shrouding of blades reduces vibrational effect. The use of heavier sections in rotor wheel reduces axial vibrations to a great extent. However, the stresses that can be allowed on the blades greatly depend on the gas temperature. The metallurgical considerations prevail in selection of blades to give light weight and long life. Special cooling arrangements for the blades may sometimes be used in gas turbines. These include supply of cooling air near the rim or use of different materials for rim and hub sections. The blade speed is selected on the strength consideration of the wheel. Classification. The gas turbine can be classified into two categories, i.e., impulse gas turbine and reaction gas turbine. If the entire pressure drop of the turbine occurs across the fixed blades, the design is impulse type, while if the drop is taken place in the moving blades, the fixed blades serving only as deflectors, the design is called reaction type. The advantage of the impulse design is that there is no pressure force tending to move the wheel in the axial direction, and no special thrust balancing arrangement is required, there being no tendency for gas to leak over the tips of the moving blades. A purely reaction turbine is not generally used. In a small multi-stage construction, the velocity change in the moving and fixed blades is about the same, the design being 50% reaction types. Such a design has fixed and moving blades of the same shape, but to the opposite hand, constituting a symmetrical stage. Accessories. There are several accessories fitted to the turbine. These are a tachometer driven through a gearbox, an overspeed governor, a lubricating oil pump, and a fuel regulator. The starting gear is mounted on the shaft at one end. The tachometer shows the speed of the machine and also actuates the fuel regulator in case of speed rises above or fall below the regulated speed, so that the fuel regulator admits less fuel or more fuel into the combustor and varies the turbine power according to demand of load. The governor back of fuel feed. If the exhaust temperature from turbine exceeds the safe limit, thermal switches at the turbine exhaust acting on fuel control to maintain present maximum temperature. The lubricating pump supplies oil to bearing under pressure. Other auxiliaries used on the turbine plant include the starting motor or engine with starting gear, oil coolers, filters, and inlet and exhaust mufflers. The turbine, and with it the compressor, is driven by the starting motor through a clutch and set up gearing. A standby motor-driven pump is also provided for emergency service. A failure of lubricating pump system results in stopping of the unit automatically. 7th February 2002 Compressor. A compressor is a device that is used to supply compressed air to the combustion chamber. Compressors are broadly classified as positive displacement type and rotodynamic type and may be of single-stage or multi-stage design. In the positive displacement machine, successive volumes of air are pressurized within a closed space. These may be of reciprocating type or rotary type. In reciprocating type machines, air is compressed by a piston in a cylinder, while in the rotary type, this is accomplished by positive action of rotating elements. The rotodynamic compressors may be of radial flow, axial flow or mixed flow type. In these machines, compression takes place by dynamic action of rotating vanes or impellers which impart velocity and pressure to the air as it flows through the compressor. The reciprocating compressors suffer from a number of disadvantages, such as inertia of moving parts, sliding friction of the piston inside the cylinder, limitation in speed, etc., and are not considered suitable for use in gas turbine plants. However, a version of this compressor is the free piston design which eliminate use of crankshaft rods and at present being developed for use in these plants. Roto-dynamic type compressors include the centrifugal, axial and mixed flow compressors which are all high-speed machines running at as high as 3000 to 4000 rpm, driven by turbines. These are designed to have high value of air discharge capacity at moderate pressure. These types of compressors are usually employed for gas turbine applications. These compressors can handle larger volume of air for same size and weight. The rotary displacement compressor with lobes and vanes on the rotor is sometimes used for gas turbine applications, but majority of these plants employ the roto-dynamic compressors. The industrial applications of roto-dynamic compressors include steel plants, gas turbine plants, chemical plants, ventilating and air conditioning, material conveying, wind tunnels, etc. They may be made in single or multi-stage configuration. The centrifugal compressor consists of a rotor called impeller, provided with vanes and moving in a casing or scroll. The inlet section at the hub of the impeller on one side, called the inducer, is curved to minimize entry losses, and is provided with vanes to direct the air to the eye. Air is given a whirling motion at high velocity by the impeller, and is thrown out of it by centrifugal force. The static pressure of air increases as it passes from the eye of the impeller to the tip. A stationary passage surrounding the impeller diffuser helps to convert most of the velocity head into pressure head as the air has a high velocity when it leaves the impeller. Further, pressure rise occurs in the volute of the scroll, so that the static pressure of air as it is released from the scroll is increased considerably. The impeller blades are made of two types: the radial blades and the backward curved blades. In the former, the blades extend straight radially, while in the latter, these are made at an angle to the radius and curve away from the direction of rotation. The change in the blade angle gives varying characteristics to the compressor. In the centrifugal compressor, the capacity varies directly as the speed ratio. The total pressure varies as the square of speed ratio, and the power input varies as cube of speed ratio. Pressure is developed independently of the load, but the volume handled depends on requirement of load. In a multi-stage centrifugal compressor, two or more impeller operating in series on a single shaft are provided in a single casing. The effect of multi-staging is to increase the delivery pressure of air as air compressed in one stage of machine is fed into the next stage for further compression, and pressure is multiplied in each stage. The overall efficiency of a multi-stage compression is lower than the efficiency of individual stage. The centrifugal compressor is superior to the axial flow machine in that a high pressure ratio can be obtained in a short rugged single-stage machine, though at the cost of lower efficiency and increased frontal area. Axial flow compressors are commonly used in gas turbine installations. The rotor of these compressors resemble those of turbines and consists of blades, which are usually made of airfoil section and set in such a way that on rotation air is moved towards trailing edge of the blades. Here a diffusing section occurs as air enters the next set of moving blades through a row of stationary blades or fixed elements. In each successive row of blades, compression takes place and air is discharged at the delivery end. An axial compressor is capable of delivering constant volumes of air over varying discharge pressures. These machines are well suited for large capacities at moderate pressures. If the impeller of a centrifugal compressor is designed to give an axial component of velocity at the exit, the design becomes a mixed flow type. Compressor used in large gas turbine plants are heavy machines. Good dynamic balancing of heavy compressor rotors is essential for safety and long life of the plant. 7th February 2003 Combustor. A combustor is a device inside which the combustion of fuel takes place. For an efficient operation of gas turbine plant, it is necessary to ensure good combustor performance. A good combustor should achieve completeness of fuel combustion and the lowest possible pressure drop in the gas, besides being compact, reliable and easy to control. Complete combustion of fuel depends upon three factors, viz. Temperature, time and turbulence. Temperature in the combustor directly affects combustion and high temperature is conducive to rapid combustion. However, high temperatures cause early destruction of the combustion chamber. Further, a limit on the temperature is also imposed by turbine conditions. An excess of air is usually necessary to keep down the temperature. This lowering down of temperature should not hamper completeness of combustion. Adequate turbulence is necessary to ensure that the fuel particles come in contact with air thoroughly. Here, again, a compromise is necessary, as large amount of turbulence results in a pressure drop. Such a pressure drop affects the turbine pressure ratio and consequently the turbine work. A typical combustor design as shown in figure 7.2 employs an outer cylindrical shell with a conical inner sleeve which is provided with ports or slots along its length. At the cone apex is fitted a nozzle through which fuel is sprayed in a conical pattern into the sleeve, with an ignition device or spark plug nearby. A fuel line conveys the fuel to the nozzle. A few air ports provided close to the location of the nozzle supply the combustion thereby to create turbulence. The rest of the air admitted ahead of the combustion zone serves to cool the combustor and the outlet gases. The combustor is best located between compressor outlet and the turbine inlet, and generally takes the shape of a cylinder. Alternatively, the can arrangement may be used in which the flow is divided to pass chambers serves all the chambers through a smaller cylindrical chambers. In this latter design the adjacent chambers may be interconnected through small tubes so that a single igniting device fitted in one of the chambers serves all the chambers. The fuel equipment consists of a fuel line and a nozzle which sprays the fuel under pressure in an atomized conical spray. The fuel is delivered to the nozzle through the fuel line and flows out through tangential slots in the nozzle, thus being given a whirling motion in an annular chamber from where it passes out through a small orifice in the conical pattern of desired angle. 2. Increase the fuel flow rates. Sometimes a number of nozzles are arranged in parallel. The pressurization of fuel is done through plunger-type fuel pumps. 7th February 2004 Generator. It is a device that generates electricity. It is coupled to the same shaft of turbine and runs at same speed to that of the turbine. The capacity of generators depends on installed capacity of the plant. The types of generators to be used depend on the purpose for which electrical energy is to be produced. 7th February 2005 Auxiliaries and controls. The auxiliaries and controls in the gas turbine power plant consist of the starting device, auxiliary lubricating oil pump, fuel control system, oil coolers and filters, mufflers for inlet and exhaust, air and gas ducts and plant control panel. Besides, there are automatic devices for alarm and shutdown. The starting device may consist of an electric motor or of internal combustion engine, and the step-up gear. Mention of these and other auxiliaries has already been made under the heading of turbine. A reference may be made to the automatic safety devices and the ducting employed in the plant. These automatic devices work during starting and normal operation of the plant. In case of any failure of the fuel supply or fire in the combustor or failure of the lubricating oil pressure, the safety alarm rings automatically and the unit shuts down. Similarly, if the exhaust temperature increases beyond a prescribed limit or the main and thrust bearings become very hot, the safety alarm rings and the unit closes down after a short interval, if the trouble is not removed within this interval. An excess of vibrations in the plant also actuates the automatic alarm and shuts down the plant's 7th February 2006 duct system. The plant duct system includes the main connection between the compressor and combustor, and between the combustor and the turbine in the simple gas cycle plant, and in addition of other such connections when additional heat exchangers are used to modify the simple cycle. The air from atmosphere, in an open cycle, enters the compressor through an air filter and ducting. It is necessary to provide clean air to the compressor to avoid early blade wear. And the duct should be adequately sized to reduce pressure drop to a minimum, since any loss of pressure reduces the efficiency and capacity of the compressor. The filters may be oil bath type or dry type. The duct connections should be short and free from sharp bends, and should use turning vanes where change in direction of flow occurs, so that the friction drops are minimum. The flow of air into compressor may produce noise which should be minimized by use of acoustical insulation. Similarly, the turbine exhaust duct should be designed to give the least possible pressure drop, as otherwise the turbine performance would suffer. The design of stack should also be based on similar considerations. Another important point regarding ducts is to support them with suitable dampers so that vibrations are reduced to a minimum. The exhaust duct and connections between combustor turbine, in particular, should be capable of standing high temperatures. 7.3 Type of gas turbine power plants. The gas turbine power plants can be classified mainly into two categories. These are open cycle gas turbine power plant and closed cycle gas turbine power plant. Open cycle gas turbine power plant. In this type of plant, the atmospheric air is charged into the combustor through a compressor, and the exhaust of the turbine also discharges to the atmosphere. Closed cycle gas turbine power plant. In this type of power plant, the mass of air is constant, or another suitable gas used as working medium circulates through the cycle over and over again. 7.4 Open cycle gas turbine power plant and its characteristics. The schematic arrangement of a simple open cycle gas turbine power plant and its representation on PV is shown in Figure 7.3. Figure 7.3, Simple open gas turbine cycle. Look at the screen. In the process shown, the cycles are 2 to 3, isentropic compression; 3 to 4, heat addition at constant pressure; 4 to 1, isentropic expansion; 1 to 2, heat rejection at constant pressure. The ideal thermal efficiency for the cycle, NT, is given by NT is equal to heat supplied minus heat rejected upon heat supplied, is equal to 1 minus 1 upon R powers K minus 1. 7.1. Where R is the compression ratio is equal to V2 upon V3, and K is the ratio of specific heat of the gas. In actual operation, the processes along 2 to 3 and 4 to 1 are never isentropic, and the degree of irreversibility of these processes and the mechanical efficiencies of the machine components greatly reduce the ideal value of thermal efficiencies of the cycle. If the air entering the combustor is preheated by the heat of exhaust gases escaping from the turbine, some heat can be recovered, resulting into an increase in the efficiency of the cycle improved. Such heating of combustion air is known as regeneration, and the heat exchanger transferring heat from gas to air is called regenerator. Since most of the output of turbine is consumed by the compressor, the actual efficiency of the cycle greatly depends upon an efficient working of the compressor. To attain higher compression ratios, it is necessary to use multi-stage compression with intercooling. Since the output of the turbine is also dependent upon temperature of gas, which expands through it, a reheating of the gas after it has partially expanded would improve the thermal efficiency of the cycle. In actual practice, all these modifications, viz., regeneration, reheating and intercooling, are combined in a simple modified cycle, and a substantial gain in the overall plant efficiency is attained. 7.5 Closed cycle gas turbine power plant and its characteristics. In the closed cycle, quantity of air is constant, or another suitable gas used as working medium circulates through the cycle over and over again. Combustion products do not come in contact with the working fluid and thus remain clean. A development in the basic gas turbine cycle is the use of the closed cycle, which permits a great deal of flexibility in the use of fuels. Moreover, working medium of the plant could be any suitable substance other than air, which would give higher efficiency. An arrangement of closed gas turbine cycle is shown in figure 7.4. In this cycle, working fluid is compressed through the requisite pressure ratio in the compressor and fed into the heater, where it is heated up to the temperature of turbine itself. The fluid is then expanded in the turbine, and the exhaust is cooled to the original temperature in the pre-cooled. It then re-enters the compressor to begin the next cycle. Thus, the same working fluid circulates through the working parts of the system. The heater burns any suitable fuel and provides the heat for heating the working fluid. In fact, this combustor is akin to an ordinary boiler furnace, working at the atmosphere pressure and discharging the gaseous products to the atmosphere. There is, thus, a great deal of flexibility in respect of furnace design and use of fuel, allowing low-cost fuel to be used. Another advantage in use of closed cycle is the choice of selecting a convenient pressure range. Once the pressure ratio has been selected, the volume of the air or the working fluid in the cycle depends upon the pressure range, which, in turn, affects the sizes of the air heater, compressor, turbine, etc. In a closed cycle, there is no restriction to keep the pressure low, and this could be kept at any suitable value, say 7.03 kilograms per square centimeter, 68.9 nCm superscript 2, amps. For the same pressure ratio of 8, the discharge pressure would be 56.24 kilograms per square centimeter, amps. These pressures would give much reduced volumes of working fluid through the plant as compared to open cycle volumes, and so there could be economy in plant size. Moreover, use of higher pressure in the heat exchanger results in better heat transfer. The precooler in a closed cycle plant is an important equipment and corresponds to the condenser of a steam plant. However, unlike the condenser, cooling water in the precooler could be heated to a fairly high temperature depending upon temperature of exit gas from the turbine, and then used elsewhere in the plant. The design of precooler is commonly of the shell and tube type, and water is the coolant commonly used. The air heater of the closed cycle corresponds to the water heaters of the steam plant, but with one important difference, that it has very small heat storage capacity. 7.6 Fuel for gas turbine power plants. Natural gas is the ideal fuel for gas turbines, but this is not available everywhere. Blast furnace and producer gas may also be used for these plants. However, liquid fuels of petroleum origin, such as distillate oils or residual oils, are most commonly used for gas turbine power plants. The essential qualities of these fuels include proper volatility, viscosity and calorific value. At the same time, the fuel should be free from any content of moisture and suspended impurities that may clog the small passages of the nozzles and damage valves and plungers of the fuel pump. However, liquid fuels of petroleum origin, such distillate oils or residual oils, are most commonly used for gas turbine plants. Residual oils burns with less ease than distillate oils, and the heaters are often used to start the unit from cold, after which the residual oils are fed into the combustor. Preheating of residual oils may be necessary in cold climates. Use of solid fuel, such as coal in pulverized form in gas turbines, presents several difficulties, most of which have been only partially overcome. Some practical applications of solid fuel burning in turbine combustors have been made commercially available in recent years. In one of such design, finely crushed coal is used instead of pulverized fuel. This fuel is carried in a stream of air tangentially into one end of a cylindrical furnace, while the gas is released centrally at the opposite end. In another design, a regenerator is used to transfer the heat to air, the combustion chamber being located on the outlet of the turbine, and the combustion is carried out in the turbine exhaust stream. The advantage is that the turbine handles only clean air. 7.7 Performance of gas turbine power plant. The ideal gas turbine cycles using isentropic compression and isentropic expansion has been described in section 7.4. Such a cycle, called constant pressure cycle or Brayton or Joule cycle, is never possible in practice due to irreversibilities introduced on account of leakages, turbulence, and internal friction. The actual processes of compression and expansion are not isentropic, and temperature of air, or gas, at the end of compression and at the end of expansion are higher than those in the case of an ideal cycle. The representation on pressure, volume, and temperature entropy planes is shown in figure 7.5. Look at the screen. The actual cycle is represented by 0.1234 and the ideal cycle by 0.1234. The efficiency of the compressor, NC, is given by the expression NT is equal to T-1 minus T1 upon T2 minus T1. 7.2. Where T1, T2 and T2 indicate gas absolute temperature at the state point 1, 2 and 2, respectively. Also, efficiency of the turbine, NT, is given by the expression NT is equal to T3 minus T4 upon T3 minus T-4. 7.3. Where T3, T4 and T4 are gas absolute temperature at the state point 3, 4 and 4, respectively. The network output, Wn, may then be written as Wn is equal to turbine output minus compressor work is equal to Wt minus Wc. 7.4. The compressor work, Wc, may be expressed as Wc is equal to MACPA, T2 minus T1. 7.5. Where Ma is equal to mass of air flowing per second, and Cpa is equal to specific heat of air constant pressure. The turbine output, Wt, may be expressed as Wt is equal to MTCPT, T3 T4, 7.6. Where metric ton is equal to mass of the combustion products through the turbine per second, and CPT is equal to specific heat of combustion products at constant pressure. Using EQS 7.5 and 7.6, EQ 7.4 becomes Wn is equal to metric ton CPT, T3 minus T4, minus Mach per, T2 minus T1, 7.7. The mass of the air is usually large as compared to the mass of the fuel. If we can assume metric ton is equal to Ma is equal to M, and CPT is equal to Kpa is equal to Cp. EQ 7.7 then becomes Wn is equal to mCp, T3 minus T4, minus T2 minus T1, 7. 8. Where Cp is the specified heat at constant pressure. Combining the EQS 7.2, 7.3, and 7.8, we get. Look at the screen. This shows that for maximum net work from the plant, theoretically, the temperature of gas at the end of compression is same as the temperature at the end of expansion. The optimum compression ratio for maximum thermal efficiency can be obtained from the relation, under ideal condition, i.e., Nt is equal to Nc is equal to 100%, as is equal to, look at the screen. 7.8 Summary. In a gas turbine power plant, a turbine, which is used as a prime mover, converts the kinetic energy of the gases into mechanical energy to drive an electric generator, load, that generates electrical power. The major components of a gas turbine power plant are compressor, gas turbine, combustor, and generator. The function of the compressor is to supply compressed air to the combustor. The function of the combustor is to burn the fuel and thus converts its chemical energy into heat energy. The function of the gas turbine is to drive the electric generator which generates electricity. Gas turbine power plants can be classified mainly into following two categories: open cycle and closed cycle gas turbine power plants. If the atmospheric air is charged into a combustor through a compressor and the exhaust of the turbine also is discharged to the atmosphere, the cycle is open. If the mass of gas circulates through the compressor, turbine and heat exchanger, it is called a closed cycle. The thermal efficiency of gas turbine power plant depends upon compression ratio, efficiency of compressor, turbine inlet temperature and compressor inlet temperature. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.